Alrighty, for problem 2, we're going to be doing some quick linear algebra review. And before we get into the actual problem, here are some quick concepts that are good to review. And so first, what is a symmetric matrix? Well, a symmetric matrix is essentially when a matrix S is equal to the transpose of itself. And as a quick refresher, what's a transpose? Well, if you look at these examples over here, a transpose that satisfies this formula actually is when after you transpose this, so you turn every single column of the original matrix into a row or vice versa, what you end up noticing is that they actually become the exact same matrix. And so this first example is a symmetric matrix. The second example is not a symmetric matrix. As you can see, by transposing it, the matrix has changed. And why are symmetric matrices nice? Well, here are some properties of symmetric matrices that will be helpful. First of all, symmetric matrices have real eigenvalues. Also, what is an eigenvalue? What is an eigenvector? We'll explain it in number 3. But essentially, you should know that symmetric matrices have real eigenvalues, and the eigenvectors of symmetric matrices, they correspond to distinct eigenvalues. And these eigenvectors are also orthogonal or perpendicular to each other. Symmetric matrices are a square, as you can tell, if you transpose like a rectangular matrix to its transpose, they're definitely not going to be the same because of dimensions. So symmetric matrices are always square, and they're always diagonalizable. Okay, and so moving on to point 3, we learned this in Math 54, or a little bit if you took 16a, but what is an eigenvector, what's an eigenvalue, and importantly, what is a singular value? So here's some quick review. An eigenvector is essentially a vector where after you apply, so here is our eigenvector x, after you apply some linear transformation a onto x, it's the same thing as if you just applied some scalar value onto x. And so what does that mean? An eigenvector is a vector that's only scaled by some constant or some scalar value when you apply a linear transformation. And so let's say like you have some vector and you apply some linear transformation, lots of like vectors like change in directions or whatnot, but an eigenvector, it only changes in its like stretching or shrinking. So it doesn't change direction unless you like completely reverse it, which is a negative sign. But yeah, it like maintains its direction. So that's an eigenvector. What is an eigenvalue? Well, an eigenvalue is just this lambda here. It's essentially this scalar lambda that represents how much an eigenvector has been stretched or shrunk. And lastly, what is a singular value? A singular value is basically just a square root of an eigenvalue. Okay, moving on to number 4. So why does the above terminology even matter? That's a great question. It's very relevant in 189 in machine learning. And here are just a few quick examples. So in PCA, which we'll learn in a bit, principal component analysis, or in dimension reduction, basically we can break matrices, if this is a matrix M, into a rotation, a scaling matrix, and another rotation. And so you may have seen this in Math 54, but essentially this middle matrix right here, it's actually a matrix that contains a bunch of like, I guess like singular values in their columns. And so probably the better way to explain it is you can essentially call it like a diagonal matrix of singular values, if you will. And so what does each like singular value in this matrix represent? Well, it represents the direction, it represents how much variance there is in data for a specific direction. And so perhaps like going along one direction, there's more variability than if you like consider some other feature along some other direction. And so as a result, you want to prioritize the features that are the most important, the ones that have the most variance. And so this is what this middle matrix can tell you, and that's what PCA can tell you, and thus we can kind of like reduce dimensions when we have like a lot of data. Okay, and eigenvalues are also kind of helpful when we're calculating like the Hessian matrix or the Hessian. That's basically, it's just a matrix with a bunch of second order derivatives, but it can tell us the curvature of a loss function and basically how steep of a change we have during like when we're evaluating a loss function. And that can also be very helpful. Okay, and so the last important thing is how do we actually compute eigenvalues? And so here is like the generic kind of like step-by-step formula for like how to compute eigenvalues. And also once you have the eigenvalue, you can then compute the eigenvectors and the singular values very easily through these two equations that we talked about earlier. And so step one is given some matrix, let's say B, first you want to kind of multiply B transpose by B to get you this matrix A. And the reason we do that is we want to end up with a symmetric matrix, and we'll see that in actually problem 2a. And why do we want a symmetric matrix? Well, they have these nice properties that we mentioned in part 2. Okay, and so once we do this, we want to solve for, we want to get the eigenvalues, which means we want to find lambdas here. And to find lambdas, well, we need to solve this equation. A of x is equal to lambda x, because this is the equation for like an eigenvector and eigenvalue. And to solve for this, we will have to set the determinant of a minus lambda I equal to 0. Why do we do this? This is like more like linear algebra stuff, so I will give an explanation after we like finish problem 2 of the discussion, that you guys can watch, but like in case you don't want to know, like you don't care why, basically you want to solve for this. And then lastly, once we solve for lambda I, which is our eigenvalue, then we can solve for sigma I. Okay, so this is actually, we ended up solving for the singular value, but I guess in this case, we're just trying to compute the eigenvalues, so this is good enough. Okay, great. And so given this background information, we can start with our problem 2a. And so here it says, prove that A transpose A is symmetric for any matrix A with the dimensions n times n. Apologies, I'm kind of losing my voice here. And so we start off, this is actually, I didn't mention this earlier, but this is a very useful formula. And so giving some amount of matrices, let's say A, B, C, and you're multiplying together, to take the transpose of this is equivalent of taking C transpose times B transpose times A transpose. And so that's going to be super helpful. What we also know is that, what is the definition of symmetric? Well, as we saw from number 1 over here, is that a matrix is symmetric when we have S equals to ST. And so if we want to prove ATA is symmetric, then we want to show that ATA, the transpose of this, is equal to itself. So how do we do this? Well, we can actually just use the property we just described over here. So A transpose A to the transpose. This is equivalent to saying, okay, we want to take this last value right over here, transpose it, and then take this other value over here, and then transpose this as well. And then this is equivalent to AT. Oh my gosh, sorry y'all, my voice literally just died at the end there, so here we go again. Okay, so we got just to A transpose A, which is great. And so now, moving on to part B. So we want to consider the matrix B equals this lovely rectangular looking thing. Okay, and then we want to find the singular values of B. And so note from number 5, we learned how to compute the eigenvalues. And so to solve for the singular value, all we have to do is we just have to square root every single eigenvalue that we get. And you can see that from the equation right over here. Okay, cool. And so we're given this matrix B is equal to 1, 0, 2, 0, 2, 1. And so first, we want to solve for B transpose B, which in here we call A, but it doesn't really matter. And so to solve for this, we do the transpose of B, which is 1, 0, 2, 0, 2, 1. And then to get to B, we just do copy pasta. And then you can solve this on your own, but just multiply, 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 and then multiply. And then what you'll end up getting is our lovely matrix 5, 2, 2, 5. Okay, and so step 1 done. Step 2, it says to solve for the eigenvalue by setting the determinant of this matrix that we got right over here minus lambda I is into 0. And so we can do that. We can say we want the determinant of, and A minus lambda I is, so if this is A and lambda I is just this identity matrix. And so subtracting lambda I from A is saying we're subtracting 5, 2. We're literally subtracting eigenvalues right over here from the matrix. Okay, and so to do this, what we end up getting is we try to do 5 minus lambda, 2, 2, and then 5 minus lambda. And so the determinant of a 2 by 2 matrix, this is also nice to know, is the determinant of some matrix with values a, b, c, d is equal to ad minus bc. Okay, and so we do ad, which is 5 minus lambda times 5 minus lambda, which is squared, and then we subtract bc, which is 2 times 2, which equals to 4. And continuing to simplify, this is equivalent to lambda squared minus 10 lambda plus 21. And some nice algebra 1, if we factor this, we get lambda minus 7, lambda minus 3 equals 0. Now, so what we can see here is that our first eigenvalue is 7, our second eigenvalue is 3, and then finally, to get the singular values of b, we just square root them. So the singular value here is square root of 7, and the second singular value is square root of 3. And so that is our answer. Okay, wonderful. You can stop here. I did promise that I would give an explanation of why we solve for the eigenvalues by setting the determinant of a minus lambda I equals to 0. So let's reason about this. Here's just some extra if you are bored. So we have a of x is equal to lambda x. And so this is just the equation for like an eigenvector, right? This is literally the definition. And so what we can say is we can actually move this to the other side. And we also multiply lambda by an identity matrix I because we want it to have the same dimensions as A. And so we can say a of x minus lambda I x. This I doesn't actually change anything because it's an identity. And we set this equal to 0 because we moved here to that side of the equation. Okay, and so now we get a minus lambda I x equals 0. And so notice how, and this is going to require you to think back to linear algebra. So if you have any generic equation, let's say we have a matrix mx is equal to 0. Recall, what does it mean for a matrix to have? Like what first of all, what is an eigenvector? Because we're trying to find eigenvalues here, or singular values. So we need to like have like eigenvectors. Eigenvectors, we don't want these eigenvectors to be equal to 0. And so basically what we're saying is we want the eigenvector x right over here to be non-zero. Well, first of all, notice that if x was equal to 0, then this is like a trivial answer, right? Like if x was like the 0 vector, then like m of 0 is 0, and that's great. However, our eigenvectors are non-zero. And so therefore, we want to try to find answers where x is non-zero. And by applying this this matrix, which is also a linear transformation, we end up with 0. What does that mean? Well, you can think about it as saying that we want some non-zero solution for x. And so this means that this matrix M is actually not invertible. Why is that the case? So here, let me write this down. What this means is that matrix M is not invertible. This is because we can essentially map multiple values, multiple vectors, multiple x's to 0. So it's not a one-to-one mapping, right? If x is our original vector and we use the linear transformation M and we map it to 0, if we have eigenvectors, we can have multiple vectors that map to 0, but then this 0 can't map back to those vectors. And so therefore, this matrix M is like not invertible. If it's not invertible, well, the definition of not invertible literally means that this determinant is equal to 0. So those are equivalent. And so therefore, we can write, if this was M, this is literally equivalent, right? Mx is equal to 0. That's saying that the determinant of M is equal to 0 because the matrix M is not invertible. Therefore, we can write this as the determinant of A minus lambda I is equal to 0. And that's exactly what we were solving for right over here. And so as a final conclusion, basically, these are all equivalent ways of saying that some matrix is invertible or like not invertible, or like we want to set a determinant to 0. And so it's always good to kind of review like what are equivalent ways of in linear algebra of saying the same thing.